Okay, hey guys, this is the same presentation that I used for the live class today, and I have a feeling it may not have worked as well as I wanted. I was actually just really hoping I'd get some more people show up so that you could ask me some questions. So you probably don't need any of this information, but it's here for just in case. What I wanted to bring to you are some problems and an introduction to the rules of density and contrast, some of the formulas that are used, and then how we will actually apply it. So let's start with density. Density is the degree of blackening of the resulting radiograph. So whatever it is that you're taking a radiograph of, the density is the degree of blackening. Yes, I said it again. Density is controlled by mass, and mass is the combination of MA, milliamperage, and time in seconds. The request for a change in density is usually expressed as an increase or a decrease. By assessing the characteristics of the equipment and the clinical condition of the patient, the radiographer must determine whether to change the MA or the time to achieve the desired density. All right, so now here is a nice example of how you actually do algebraic functions for mass. When you set a manual technique for various procedures, there's two factors, milliamperage, MA, and time in seconds. That milliamperage or MA controls the amount of radiation. The time of the exposure controls the period for that particular quantity or the amount of radiation that will be emitted from the X-ray tube. So you can pick all the MA that you want, but you're only going to get it for a certain amount of time by the time that you set. The time of the exposure controls it, but together mass is an equal amount. So that's why this is drawn this way. So here's mass right here. So you can change your MA and your seconds in whatever quantities that you want, but they will still only equal one mass. Therefore, because of the differences in your patients and your equipment, it's sometimes necessary to change one or the other without changing the desired density. Changing one or the other is what we call the reciprocity law. So let's look at that a little closer. Here's that same pie, if you want to call it that. So for mass, you want a combination of MA times time. If you only need your MA, then you take the bigger portion of mass and divide it by seconds. That will give you your MA. If you don't know your time, but you have these two factors, again, take the bigger portion and divide it by MA, and then you will have time. Now, if you have certain problems, like such, a radiograph is produced using 100 MA for 0.4 seconds. What is the mass? So that one's simple. Mass times is equal to MA times time. 100 times 0.4 is 40 mass. Now, if you took this same problem and you said, now I have 40 mass, but I can only use the 200 MA. So now I want a different time. So what would you do? Seconds or time is equal to the mass divided by MA. So 40 divided by 200 is 0.2. It's just that simple. And even though it is that simple, you can get really confused if it's a simple word problem, which is what you will more than likely encounter are word problems, not just black and white fill in the blanks. So if we want to increase density of a radiograph by 40%, and when I said density is usually talked about with an increase or decrease, it is usually by a percentage. Now, the original technique was 100 mass at 400 MA for 0.25 seconds. So I've given you all three values right there, but we want to increase the density. So to increase the density by 40%, we take 100 mass times 40%. Right here, if you don't know how to change that percentage to a decimal, then you need to go back and review some math problems. But 40% is 0.4. I gave you some examples and gave you the links to two books that the library has for you that you can use, but this goes back to simple math. And if you're told 40% on a problem later, they're going to expect that you know how to change that. So 100 times 0.4 is 40. Then you take that 40, so that's not your answer. We want to increase by 40%. 40% is 40. We add that to the original 100. So your answer is 140 mass. I can guarantee you that if you have a question like this on a test later, the number 40 would show up as one of your answers because there was, 40% of 100, that's 40. So, but that's not the total. We have increased the density by 40%. So make sure that you do that way. If you decrease the density of a radiograph by 30%, the original technique was 300 MA for 3/5 of a second. Now I've gone and just given you 2 of the variables that you need. Oh, and I was really mean. 3/5, what is that in a decimal form? To get a decimal for 3/5 seconds, 3 divided by 5 is 0.6. Okay? Your new mass, or your mass, is 300 times 0.6. So we had that one, we had that one. Now we have all 3. So we have 180 mass. Now go back to the original question. Decrease the density by 30%. 180 mass times 30% is 54. What are we going to do with that mass? We decrease. So 180 minus 54 mass, your answer is 126 mass. So again, you may actually see all 3 of those answers as possibilities. 180 mass, 54 mass, and 126. You're not going to have these step by step, but you need to be able to figure it out, and that's what you call critical thinking. Make sure that you understand the word problem and how to get an answer. Now, let's look at some alternatives. It's not always possible to find an MA in a time that produced the exact mass. It's often necessary to choose an MA in time that give the closest possible mass desired. Now, for this particular one, we have 300 MA and 126 mass. So to find out the seconds equals mass divided by MA. Seconds is 126 divided by 300, 0.42. Now let's go back to what I just said. Sometimes these numbers are not exactly there, but and I'm still using the word dial. You definitely don't have a dial any longer, but if your selection most likely doesn't have a 0.42 set up, it may have a 0.4. A 0.40. So from there, it's 120 mass. A loss of that 6 mass is okay, especially in this particular range. Between a certain amount of mass that you use, losing 6 mass would not be a big difference. There has to be a change of at least 30% to produce an appreciable change in density. So what I'm trying to get at is, even though we figured this out and that's the answer, but this is the closest one available, that one would work. That is an alternative to the time that you need for that radiograph. Here's a problem. A radiograph needs to be repeated using 60% of the original density. The original technique was 85 kV, 200 MA for 4/5 seconds. We got a lot of things going on. What I went ahead and did is give you the 0.8 for 4/5. 4 divided by 5. That's your answer for that, just for that part of the question. So you have to determine the initial mass. 200 times 0.8 is 160 mass. Now, we got to find 60% of it. Determine the new mass. 160 times 60 is 96 mass. Now guess what, folks? Don't read this and say, oh, I got to increase by 60%. Using 60% of the original. So you get your 60% and that is now your answer. So please make sure that you read the entire question. And I also want to point something else out. They threw in 85 kV. Nowhere in here has it talked about contrast. We're only talking about density, so we didn't even care about that. And a lot of times word problems are thrown at you with different numbers that are not useful to the problem that you're trying to solve. So we now have 96 mass. Now let's go look at the possible combinations. Which ones of these would you choose? Now, one of the things I want you to think about is First of all, you've got to say, so what if these were your answers? If these were, okay, go back. 96 mass. Which of these combinations do you want? Well, first of all, find out the mass. 100 mass, 100 mass, 90 mass, 100 mass, and 100 mass. If there are no extenuating circumstances involved in your question, and it just says which ones of these are possible, there's probably a any of the above or all of the above, because any of those will work. But what I want you to know is that they would probably give you these combinations if there was something about your patient. So pretend with me here for a second. Your patient cannot hold still. And if you had these particular, doesn't even matter what the body part is that you're x-raying, but if you have problems with your patients holding still, you would want to pick the one that has, right here, 0.1 seconds. So 0.1 seconds is the smallest amount of time as compared to any of these. Now, yes, is 0.1 pretty close to 0.125 or 0.15? They're close. But go for the lowest if that is possible. You do need to remember, though, that 1,000 mA may be a lot for your equipment, so make sure that your equipment can actually handle that too. So that would make a difference also. All right. Now let's go to contrast. Contrast is defined as the amount of difference between the blacks and the whites on a radiograph. Scale of contrast is referring to the number of tonal values from white to black. And when you have tonal values, that means the shades of gray. When you think about contrast, or you may hear the word contrast, you also need to know what it means to have a short scale, few shades of gray, or a long scale, which is a lot of shades of gray in between the black and the white. So short scale, short. Long scale, long. Big numbers. Here's another way to say it. Contrast can be called the difference in density between two areas on an image. If it's high contrast, large density differences. Low contrast is small density differences. If you have a grayscale, long is low contrast, short is high contrast. For high contrast, that is a short scale of contrast. That means there's not very many variations between the black and the white. High contrast, very black and white, low kV exposure. This is, it's appealing to the eye, but it's seldom the ideal choice because diagnostic information can be lost. A low kV image is going to have a high contrast, short scale, and it's usually used for extremities. Here's a low contrast. A film with low contrast produces images with less contrast and a longer scale. And look, here's our black, here's our white, and look at all the differences in between. That's what makes a long scale of contrast. But it's also low contrast because it's not contrasty. Here's an image of the gray that's right in the middle, and you want to count the shades in between. These images are usually made with high kV. So the higher kV, these are the ones that usually yield more diagnostic information, although the image may not be the most eye-appealing to radiographers. And if you ever work with radiographers like me, and let's just say at my age, we're used to the more contrasty images than we are the grayscales. Here's the two together: low contrast, high KVP, long scale. Here's high contrast, low kV exposure, and this has a short scale. This is a nice image also. This actually is a step wedge that was placed beside this fake knee. And by doing this, these are different levels or thicknesses of the aluminum. So you're seeing how many show up. Over here you see more. So that means this is a longer scale. This is less contrast. This is more contrast. Short scale, long scale. Okay. With KVP, Even though it's not generally considered good practice to change the scale of contrast, it's sometimes necessary to obtain more diagnostic information. So if you are told to change an image because of the contrast, then you want to know that it's the KVP that you need to change. There's a 15% minimum change needed in the 60 to 80 kVp range. And with that, that means that 15% increase would mean it doubles the density of the image, whereas a 15% decrease halves the density. So those two things go together. If you're told to change the density only to change the contrast, but they don't talk about maintaining the density, this is how you can do it. Here's a 15% increase. So we went from A to B. So this knee has a shorter scale of contrast, so we went to longer. It has high contrast, we went to lower, but it also doubled the density. So by doing that, we increased the KVP, and only the KVP, by 15%, and by doing that, then we have created a different image with more density. This one to me is a little easier to see. This is a 15% decrease. So we've taken this image of this hand, which is high KV and low contrast. So it's a longer scale. But we decreased our KV. Now we have a higher contrast and a shorter scale. This one you can see the differences in, and I'll tell you why. This knee x-ray was probably more in the 70 to 80 kV range, whereas this was only in the 50 kVp range. So the 15% decrease at this kV actually made more difference than the other one did. Now this is for if we were changing an image just to change the density, but also changing the contrast. What if we want to maintain density? If we adjust the KVP for contrast, but the density was okay, then you have to change the mass also. If you increase your KV by 15%, you have to half the mass to maintain density. If you decrease KVP by 15%, you have to double the mass to maintain density. So let's look at this math problem. A radiograph is made using 100 kV at 40 mass. It's necessary to double the density, but you cannot change the MA. What change in KV would double the density? So you've already got the question right here. You have to change the KVP because you cannot change the MA. But you want to double the density. So if you double the density, you get 15% of 100, which is 15 kV, and you add it to the kV. Your new kV is 115. Now if we want to decrease, radiograph at 90 kV at 30 mass, you need to decrease the density, but you cannot change the MA. What would you do to half the density? 90 kV times 15% is 13.5. To decrease, we subtract. Our new KVP is 76.5. Make sure that you read the question, decrease. I highlighted these words. It's not going to be that way on an exam. So make sure you read it, you understand what it wants you to do. Now what about a math problem and it tells you to maintain density? A radiograph has too much contrast to be diagnostic. The original technique is 68 kV at 80 mass. What new technique would you provide a longer scale of contrast while maintaining the density? So let's do one at a time. The original technique, too much. We want a longer scale. So to get a longer scale, we're going to have to increase the KVP. 68 by 15% is 10.2. To increase and get a longer scale of contrast, we add it. So now our KV is 78.2. But we're not done. Read the rest of the question. We did make a longer scale of contrast, but we want the same density that we started with. Because this also increased the density, now we have to half the mass to maintain that density. So 80 mass times a half, or you could have said 0.5, is 40 mass. That's how you work that problem. Now we want to do another one. A radiograph does not have enough contrast to be diagnostic. The original technique is 90 kV at 40 mass. What new technique would provide a shorter scale of contrast while maintaining density? So 90 kV, no matter what, we're going to change something by 15%. 15% of 90 is 13.5. But we want a shorter scale. We want less kV, so we subtract. Our new kVp is 76.5 kV. But it also says we want to maintain the density. Because this just halved our density, now we have to multiply the mass by 2, and we have 80. Now, this is actually the last slide on this. That's all I had for the live class that I also put together. I want you to go over these, listen to these, and then there is a math problem. So I'm going to do this. Let's escape. And let's do this right here. Under supplemental info on Blackboard, I hope this is showing up for you. Down on the bottom is something called math problems. You can actually grab this right here, and I'm not going to give you a grade because it's nothing I can do to add to the grade book, but these would really help yourself if you want to do that. Now, these are the two texts that I talked about also that you may want to actually go and check and see if you still understand some of those basic math questions, okay?